So let me introduce our speaker today. Today's speaker is actually also the usual chair for this journal club. It's Kishor Bharti, and he's working with me on essentially foundation of quantum mechanics all the way to machine learning. So, and recently, he's been very active in quantum machine learning, and he has initiated this journal club, and he's going to present today a blueprint for practical quantum advantage, which is joint work with Tobias Howard. Kishor, you can start.
Thanks, Greg, for the introduction and volunteering to chair the session. So yeah, I mean, as you can see, the title is a blueprint for practical quantum advantage, and I mean, the talk that I'm going to deliver today, it's based on some of these works which are here, like the archive numbers and all, and. So yeah, I mean, since most of us are from CQT, I mean, there's no need of much introduction apart from the fact that this is the place and this is the group where I work, and my mentors are Vlatko Bedral and Leong Chuan Kwek, and this work is mostly with Tobias Hogg, and yeah, as Kwek mentioned, I mean, I have worked on a few things. During my PhD on in quantum foundations and computation in AI. But in this talk, since it's a quantum machine learning journal club talk, I will mostly focus here and basically talk about NISQ algorithms. So I will explain what NISQ algorithms mean. And in case you are interested in collaboration or something, these are my research interests. So we can possibly find some overlap, and if there is one, then I will be very happy to collaborate and work with you. Okay. So yeah, I mean, there was this experiment recently, it happened almost 1.5 years or something, which Google performed, and that was basically a circuit sampling task. And what they demonstrated that on some using some noisy quantum computer, which means it's not error corrected ones, they can perform a task which takes 200 seconds on their device. The same task, if you perform using state-of-the-art supercomputers, that will take 10,000 years. Though it's a bit debatable, and a lot of work is being done, and many papers came which kind of claim that this 10,000 years can be further reduced to 2 days or whatever, even less recently. And people are using various tools and techniques to really understand that how difficult this experiment is. So if you really want to look at, there was a paper recently on archive by Adam Booland and others, where they looked at the frontiers of noise in the NISQ era and all. But this experiment anyway was very useful. I mean, for experimental purposes at least, a good engineering achievement and all. And people talked about it. So, for example, if you want to look at an opinion post by Scott Aronson, you can refer to this New York Times article. Then with a different setup, using photons, I mean, quantum computational advantage was recently, very recently shown by the group in China by Jian-Wei Pan and others. And still, I mean, we don't quite understand how difficult it is to really perform this experiment using simulate this experiment using classical devices. And the hardness of spoofing some benchmark, for example, here it was something called cross entropy benchmark. I mean, similarly here, there is some benchmark involved, some other version of benchmark, and we don't quite understand how difficult it is to spoof basically the quantum computational advantage shown by this experiment. Anyway, that's not the purpose of the talk. Like so for the moment, like a scope of the talk. So for the moment, let's assume that we have some kind of experimental advancement, and the devices which are out there, they are performing something which is in fact classically intractable. Now, and also, like, I would like to comment, I mean, these quantum supremacy experiments are more like those Bell inequality like violations, where people were not believing in the beginning with all the loopholes and all, but over time, like we believe that, yeah, like loophole free Bell tests were performed like in 2015 and like later and so on. So yeah, this will improve with time. So the starting premise is that, like there are some devices which are powerful enough, which can perform a task, which are classically intractable. So, but those tasks that they performed, I mean, they are very contrived examples, and we do not yet know any practical application, I mean, like for any industrially relevant task. And John Preskill basically suggested, I mean, like not him, like many people talk about it, that there are some dangers of the hype and whatever is, like coming to the field. And we know that if let's say that all this money or whatever is coming to the field, and if we do not deliver something, let's say in like soon enough, maybe like, I don't know, 10 years or whatever, I mean, it's very difficult to make such statements. There is a possibility of quantum winter. And we need to move beyond a quantum supremacy. Like we need to, look for some practical applications. And this is where the idea of NISQ comes into picture. So John Preskill in 2018 proposed this word noisy intermediate scale quantum. He mentioned that we are in an era where devices are noisy. They don't have, like, I mean, the quantum compute, the qubits that we have, they lack error correction. So we don't have logical qubit. We have something called physical qubits, like many of them, like maybe 50 or whatever. So they are noisy and they are like not very big, like they are intermediate scale. So in this NISQ era, can we do something useful? And he has like mentioned that there are certain areas where we can look for advantage and so on. And in last few years, the field has really exploded. Like the lot of work has been done and all. And recently, I was involved in some review with researchers from MIT, Harvard, Toronto, like University College, Imperial College London, and so on, and CQT. And like this review basically talks about different aspects of the NISQ algorithms, like the algorithm which you design for these NISQ devices. It has more than 700 citations, and still, like, I mean, we could not cover everything. Like, I mean, we still got some emails, some important emails which we missed, because, I mean, yeah, it's really like very, I would say, highly active field at the moment. Yeah, so you can have a look and maybe, like suggest something which you find is missing there, or something should be there, and so on. So yeah, I mean, so the point is, like, one can ask, like, where should one look for practical quantum advantage? And some of the areas which are like relevant are quantum simulation, combinatorial optimization, quantum chemistry, machine learning, and so on. Now, among them, like, I mean, the two which is in particular, like, I mean, I find them hopeful is this thing called quantum simulation. And the other is something called local Hamiltonian ground state problem, which is QMA complete problem. What it means that it's even difficult for quantum computers. So indeed, you can use them in some race with the classical devices and see whether they offer advantage over the classical devices. Moreover, this local Hamiltonian ground state problem has application in solid state physics, quantum chemistry, and combinatorial optimization. So, for example, the combinatorial optimization problems, you can like map them to some diagonal Hamiltonian, like only polyjet terms and so on, and then use local Hamiltonian ground state problem to solve it. Yeah. So basically, these are some areas, and one can hope to get some advantage in the NISQ era, if at all possible. So one of the, I mean, the canonical algorithm which has been developed in the NISQ era for NISQ devices is this variational quantum eigensolver. So if I talk about it like a very high level, what it is nothing but the variational principle of quantum mechanics for finding the ground state. So what you say that you have some ansatz that you prepare with only polynomially many terms, and you know that the ground state is the minimum energy eigenstate, and you cannot go beyond that. So maybe you can tune the parameters of your ansatz such that the energy decreases. But because you know that you cannot go beyond the ground state energy, then the approximation that you will find will be, like lower bounded by the ground state and the ground state energy. So in that sense, you can use this variational principle as a kind of a guarantee to prepare, or let's say approximate, or basically approximate numerically, or in some cases like in experiments, like prepare the ground state and ground state energy of some Hamiltonian. But the main problem is the representation. Like, I mean, can you, as the number of qubits and so on increase, can you like represent them nicely? So this is where quantum computers come in practice. So like what you can do that, like what this paper suggested is that let's use a quantum computer to prepare the ansatz quantum state. So you have some circuit which has, like a small number of parameters, like polynomially many parameters. And you use that ansatz circuit, which has this theta, to prepare psi of theta. For the psi of theta, you estimate the loss. So you're a Hamiltonian, which is a sum of a small number of poly terms, like tensor poly matrices and so on. And you calculate the expectation value of each of the poly matrices, and then using that, you basically calculate your expectation value of the Hamiltonian. And once you have this expectation value, then you can feed that information to the classical device, and it tells you like how to tune the parameters. Now, using some gradient free approach or gradient based approach, you can tune the parameters, which changes the quantum state again, and then you can again calculate the loss, and you can update the parameters and so on. This algorithm has really, I would say, like, I mean, has been one of the, I would say, like our biggest hope for quantum advantage in the NISQ era. And but one problem which you can very easily spot here is that the classical optimization, when you say update the parameter, is highly non-convex. And how do you update the parameter? It's not very well specified. It's non-convex program, but what kind of non-convex program? And it does not correspond to any well-characterized optimization program. So which means the whole setup is like highly heuristic, and you can in fact experiment, like try numerical, you can play with numerical experiments and so on and see like how it performs. But saying something rigorous and all and making rigorous statements will be very difficult. Another algorithm which is like, so this was for the ground state. The other algorithm is for like Hamiltonian simulation, is this variational quantum simulator algorithm, which was developed by Lee and Benjamin, like Ying Lee, who was earlier working with Quake at CQT and later joined Simon Benjamin. And they like came up with this algorithm called variational quantum simulator. And what it does is that you have some Schrodinger equation, and you want to simulate the evolution of some quantum state psi t using some quantum computer. Now, in the ground state problem, you have a variational principle called the static variational principle. Here you have some different kind of variational principle, which is like dynamic variational principle. Now, there are three different variational principles, like, I mean, commonly used in the literature, like in quantum chemistry and so on. But two of the most popular are Dirac and Frenkel variational principle and McLachlan variational principle. Actually, if your parameters defining the ansatz are complex, then all three variational principles are identical. So yeah, I mean, that's something high level information. So the idea is that what you can do, that you can represent your quantum state psi using some parametric quantum circuit phi theta t, and if you and there is a way in which if you tune your parameters theta, then that can help you mimic the evolution of the quantum state on the quantum computer. So for that, the way you can change your theta has to satisfy some condition called this condition, which leads to basically the following differential equation, which is differential equation with a small number of parameters, unlike this large dimension differential equation. And you can solve it using the information of this overlap matrices Aij and Ci, which you can get from a quantum computer to update the parameters theta. So once you have the new theta parameter, you can feed it again to the quantum computer, and then the quantum computer basically gives you A and C matrices, and then you again get it to feed it to the classical device, and it changes the theta. So you keep on changing the theta such that it mimics the evolution. But one of the problems which you can straightforward see here is that this variational principle at least is not implementable using parametric quantum circuit, because this A and C, they can be complex, and as theta changes, what can happen that under the evolution, like the theta can become a complex number. But normally, in parametric quantum circuit, the theta basically correspond to some gate angles or whatever, which has to be real valued, which means it cannot be implemented on the current devices. So what Simon Benjamin and Ingley proposed is this McLachlan variational principle, where you get not this one, but a modified version where you take real part of Aij and complex part of Ci. And here, if you start with thetas which are real, then you always, it remains real. This is all good, but there are some problems with this method, which I will explain. First problem is this quantum classical feedback loop, which I particularly don't like, and many people in the community share this feeling. Like you have some quantum computer, and then it goes to you do some measurement, it goes to the classical computer, new parameter, quantum computer, and so on. This feedback loop really makes everything super slow, and we cannot hope to attain some advantage in this setup, because even for a small systems, it takes like a lot of time. Because first of all, when the classical computer is doing something, the quantum computer is sitting idle. When the quantum computer is doing something, the classical computer is sitting idle. And this is not good, because basically the resources are being wasted when each of them are, and there are many feedback loops going on, and it really slows up the whole process. More on top of that, let's say if you are somebody who access the devices in a cloud, it's more messy there, because when you go, it's on a random day. When you go, you have these many jobs in queue, and if you send the classical, if you send your job, it's in queue, it gets executed, it comes back, and then you perform something, and then it goes back again, and then it has to wait for the jobs to get for executed. And normally it can take for days, or even if you go for large number of qubit, it can take even 15 days to 1 month, and so on. So yeah, it's a very gloomy situation with this kind of feedback loops. So the first thing we need to do is remove these feedback loops. We want to do, or maybe minimize the number of feedback loops, and people have been doing trying to minimize and all, but what I advocate is removing them altogether. They are not really good for I would say achieving quantum advantage with in the NISQ era. The other problem which I don't quite like, and many people share, is this control unitary. So for example, if you have to measure the overlaps, as you see here, this A and C matrices, you need to do some kind, because these are complex numbers, you need to do some kind of control unitary experiment, which depending on whether you want the real part or imaginary part, you can tune the value of B here to be 0 or 1, and you can get the outcome. This is called Hadamard test. And but the problem, it's good, it looks pen and paper, on pen and paper it looks very nice and all, but really implementing them in the experiments, I do not expect that we will have a technology in the near term. Maybe experimentalists can enlighten me more, that you can rotate the state of, let's say, 20 qubit or 15 qubits just by the taking, using your 1 ancilla qubit. And yeah, I mean, this is also something. These algorithms which use this control unit rays are not really good. Like, I mean, and I see many papers coming in literature where people are rampantly using this kind of control unit rays and calling them NISQ algorithm. But I personally don't believe them to be like really current term NISQ device. You can call them near term, but that's also subjective. Like how many years you really believe it will take for us to have, like this kind of multi-qubit control unit rays. Other problem is with respect to trainability. So like, I mean, as you increase number of qubits, what you suffer from is something called the barren plateau problem. So like normally what you do that you measure some kind of expectation value as a function of theta, and let's say with some theta k parameter, if you calculate the gradient, if the circuit has has been initialized randomly, it can because of some two design structure, which I will not go in detail, like you can ask me later, I can explain and all, you can prove that the gradient vanishes. Moreover, the variance decays exponentially in number of qubits, which means that the landscape becomes like almost flat, and only near the solution you get like you get something like some kind of valley. So basically it's a problematic situation, and many papers came last year, like from Los Alamos group, and then from Nathan Weave and others, and then also like where they showed that this is really a problematic situation. And in the NISQ era, you can have like noise induced barren plateau, you can have entanglement induced barren plateau, and then also the gradient free approaches, like I mean, they seem to be not very good in this kind of scenarios. So like one of the arguments which many people put that maybe gradient free optimization can help you in some way. But the way like this gradient free optimization work is that, like for example, the simplex kind of methods is that they take 3 points. So like if you have some kind of like let's assume that there is some gradient, and so you take like 3 points and you compare which of them are like smallest, and then you move in that direction using some simplex kind of algorithm. But assume that if the landscape is flat, and if you take 3 points and try to compare, there is no hope. I mean, it's just a very hopeless kind of scenario. More, I mean, like with my colleagues at Caltech and at CQT, Patrick Raventros, we showed that with linear system also you have some kind of barren plateau problem, which is like a new kind of barren plateau. It's more like problem-induced barren plateau. With Minshikim and Tobias Hogg, recently we proposed ideas based on quantum Fisher information to tackle such challenges. But still, I mean, I am in particular like not very hopeful with the current scenario, and more work needs to be done to understand it. So yeah, I mean, there are many problems, like the optimization program is not well characterized. There is like training issues. There are like a problem with this control unit rate. There is this feedback loop, and we need to remove many of them. Yeah. So using many ideas which were present recently in the literature, I came up with this two algorithm called quantum assisted eigensolver and iterative quantum assisted eigensolver. And for these two algorithm, I do not claim like complete novelty, because like some of the ideas were present in some paper, some of the ideas were present in some paper, and so on. And I kind of like a cook, I would say, like I put them together and came up with these algorithms where I take care of many of these problems. And over time, we worked on these ideas and developed algorithm for Hamiltonian simulation. And then we have also algorithm for like linear system of equation, and algorithm for open system dynamics, Gibbs state preparation, imaginary time evolution, and yeah, like time dependent Hamiltonians and so on. And then like, I mean, with some of the quite brilliant students which Quake had recently, we are developing more algorithms, and get tuned. Like, I mean, you will see more things coming in future from us. So if you can take some kind of take away message from this talk, is that the algorithms that we are developing, they are based on hybrid states. So I will explain what are hybrid states. They are quantum states are a special case of hybrid state. And the rationale is this, that if you are using some kind of hybrid computing, it's better to use hybrid state and not like classical, not like quantum states, because yeah, they can help you in some way. These algorithms do not have any classical quantum feedback loop, which means they can be like implemented exceptionally faster than their variational analog. So for example, like recently we implemented these algorithms, and our algorithm can be like not a very optimized version, can run in minutes. On the other hand, if you try to run uh, uh, variational quantum versions, they take like days for the implementation. Like for a small case, like 2-qubit, 3-qubit case I'm talking about. So forget the case, like when it goes to a large number of qubits and so on. And then also, like, these algorithms do not have the barren plateau problem. Like, they circumvent the barren plateau problem by construction. These are effectively a sampling based method. So you just need to use the quantum computer for a sampling task. And the current existing quantum computers, we can believe that they are good for sampling. So yeah, I mean, it very much fits with the current capabilities. There is a systematic approach to build the ansatz. So you use the structure of the Hamiltonian to build the ansatz. And they do not require any controlled multi-qubit unit trace. So yeah, like pretty much consistent with the existing like capabilities. So yeah, I mean, like at the moment, if you have any question or something, like please stop me, because like that is so far I put the motivation and the take home message and all, and after that the technical part will start. So if you want to stop me or something, like most welcome. Okay. Since there are no questions, so I will move forward. So basically, like, I mean, this is the setup. What you say that your Hamiltonian is linear combination of unitary. I mean, like, this is a starting assumption, and this is a very, like, I would say, very fair assumption, like a valid assumption. Like, I mean, if you think most of the spin Hamiltonians, or the most of the Hamiltonian that you look in the combinatorial optimization problems and so on, they can be written like this. In fact, the tensor poly basis that forms a basis. So you can write any Hamiltonian in this form. So this is without loss of generality. You can start that with this assumption. In fact, like, I mean, the two local Hamiltonian problem has been shown to be like QMA complete. So that's, in fact, I would say it's a very powerful class of Hamiltonians. And you can, in fact, represent any Hamiltonian like this. Now, what we say that let's use some kind of a state called hybrid state. So your hybrid state is a classical combination of quantum states. So this eta alpha which I use is not really a quantum state, but there are quantum state chi I, and you put some weight on them. So you have the weight alpha 1 on chi 1, alpha 2 on chi 2, alpha 3 on chi 3, and so on, alpha n on chi L. And what you say that let's use this hybrid states and use this Hamiltonian H to calculate expectation value of the Hamiltonian, which is basically take your H and you put like get this ansatz and the bra from the other end, and you will get some term like alpha dagger d alpha. But I use transpose because I just realify. So like you can go to like 2n dimensional space, and whatever is complex, you can make it real. So without loss of generality, let's use a transpose for mathematical simplicity, like, and that's without loss of generality. So you have some terms like alpha coming from here in the on the left hand side, and from the bra part, and this is something from the ket part, and you get some D matrix, which is basically you get from this beta ui, and then chi n from the left, and then chi m from the right. So you minimize alpha transpose d alpha subject to the normalization constraint. Like you want this to be a valid quantum state, which means that alpha transpose E alpha equal to 1, where E is this overlap matrix. So basically your goal is to minimize energy subject to the normalization constraint. Notice that unlike VQE, where your optimization program is simple, like some non-convex optimization program, and you do not say anything about what kind of non-convex optimization program, here your optimization program is well characterized. It's a quadratically constrained quadratic program, QCQP. And later I will show that you can prove many nice statements about QCQP and so on. In fact, in the optimization theory, QCQP is a well-studied object. So you can use ideas from optimization theory to make statements about this Hamiltonian ground state problem with respect to the ansatz that we have. Yeah. So another ingredient of our algorithm is that like normally it's better to feed as much information of the problem in the ansatz that you build. So we have Hamiltonian as a linear combination of unitary. Let's use these unitaries to build the ansatz, because I mean, if you try to search anywhere, basically you will be lost. So, and Hilbert space is a big space, and you do not want to get lost. Like, I mean, all these barren plateau problems and all, I see them as manifestation of not much information. So if you do not have information, obviously you will suffer. So let's use the information, and that information will help you to design the ansatz and like get the answer and so on. So what you use is that you use all of these unitaries which define your Hamiltonian to build a set called this math BB formative. So you have this set of unitary, and you have some initial quantum state psi which some experimentalists can implement in their laboratory. What you do that you take this psi and you use the unitaries which define your Hamiltonian to define the set of quantum states called k moment states, where you from this set you take a k of these unitaries and act on psi. So the one moment state, a set of one moment state will be psi and u1 acting on that, psi u2, psi u3, and so on. Two moment state will be something like psi u1 square, psi u1 u2, psi u2 square, and so on. Similarly, k moment state will be psi and k of such unitary acting on that, and all such set you call the k moment states. The set where you do not act by any unitary, that's a singleton set, and you call that zero moment state. The cumulative k moment state can be defined to be the union of all these k moment states. And what you say that your ansatz with a particular value of k can be written as linear combination of cumulative k moment states. Now notice that if these unitaries are, let's say, tensor polys and all, then basically all of the quantum states, they are Pauli related to your quantum state psi, because product of Pauli string is a Pauli string up to a phase factor plus minus 1 or plus minus iota, which can be classically computed. So you just need to prepare one quantum state psi, and then other quantum states will be just one layer of Paulis after that, which can be like very easily, which is like a bread and butter for the currently available quantum devices. So the algorithm is very simple. It's like a 3-step algorithm. For the IQA part I'm talking, later I will talk about the QAS and other algorithms also, which have like similar structure and all. So what you do that using this cumulative k moment states, you define your ansatz as a linear combination of cumulative k moment states for a particular value of k. This step happens on a pen and paper. No device is involved here, like it's mathematics. The second step involves calculation of D and E matrices. Notice that this can be complex, but you do not need any Hadamard test or control unitary to evaluate them. Why? Because you have something like psi, and then psi from the other end, and then product of many polys. Now, if you take the product of many polys, you will get like some free factor like plus minus 1 or plus minus iota. So that you can anyway compute like very easily. What is difficult to compute is this psi and then poly string and psi. But that is like sampling of the quantum state psi in a poly-rotated basis, which you can very easily do. So you do the sampling task on the quantum computer and you get D and E. Once you have D and E, then you run this QCQP on a classical computer. And yeah, and you are done, like basically. So in fact, you will see later that we are writing a paper with one of the students, one of the brilliant students which Quek has, to make practical use of the Google's data. So Google data, though it's useful, though it's not very, it's basically useless for all practical purposes. It was like a good theoretical experimental demonstration of the hardware capabilities and all. But can you make some relatively not so useless statement out of that experiment? And you will see that we have something coming out in future where we will make some statement. You can justify the ansatz using imaginary time evolution. I will not go in detail because like time is running fast. But if you have, if you want to talk to me personally, I can explain and all. actually you can explain like why do we have this kind of ansatz and all. It's related to this idea of Krylov subspace, which is a very well studied object in optimization theory, like in classical theory and all. And there are many open questions which we get from here, and like this help us, like make more rigorous and meaningful statement in the NISQ era. So in the NISQ era, mostly what I see that people are just running certain things and like publishing papers and all, which I particularly like not very much like. And I think we need to make really meaningful statements, we need to have like algorithms which are like as transparent as possible. So if you see, we have like in our algorithms, like the first step is like it's all transparent. The second step is like sampling task, which you can study very nicely, like a lot of nice papers are being written. And the third step is basically QCQP, for which you can study, like effectively and all. For the dynamical evolution, like I mentioned earlier that the Dirac and Frenkel variational principle you cannot apply, but in fact on the gate-based implementation which Simon Benjamin and Ingley had. But in our approach, because we use these alphas to be complex parameter, you can use any of those variational principles. And what we show that again, you do not have any feedback loop and so on. And there is no need to perform any Hadamard test. Like because you tune only the classical parameters, like you have there is no barren plateau by construction, no classical quantum feedback loop, and then the ansatz can be systematically generated and all. In fact, recently we showed that in fact, this differential equation, it can be formalized as a QCQP. So it's personally quite satisfactory for me that both the Hamiltonian ground state problem as well as the Hamiltonian dynamics, we can formulate them as QCQP. And I mean, it's like first time that we like some in the literature that we have managed to relate this problem with QCQP and like and further relate them with SDPs and so on. And get tuned, we have some work coming up on a projective quantum assisted simulator where we use these ideas, like use them to formulate as QCQP and so on. So maybe in a week or something, you might see some paper coming on arXiv. Moreover, you can use these QCQPs and do some kind of semi-definite Lagrangian relaxation, which turns out to be an SDP, which are widely well-studied optimization programs. You can also do like direct semi-definite relaxation and like study this classical optimization. Moreover, you can also tell like you can also give sufficient condition for a local minima to be a global minima, which can be used as a solver for a stopping criteria. So these kind of statements are like totally missing in the VQE setup and all. Moreover, you can show that VQE is a special case of IQAE. So you can do that you can in your ansatz, each of those quantum state you can put some theta parameter and you can tune them and like show that in fact they like whatever statements they make, it trivially reduces to like a special case of the IQAE algorithm. The variational quantum simulation algorithm similarly can be shown as a special case of the quantum assisted simulator algorithm. We also propose this idea of called hybrid density matrix, which is like a generalization of the hybrid quantum states. And using that, we propose this generalized quantum assisted simulator where we give algorithm for generalized time evolution, nonlinear differential equation, gives state preparation, and basically as you see, we provide a bucket of many algorithms. So we see that many algorithms can be formalized like this, and so on. So like do check these papers and you will find maybe something useful there. You can do imaginary time evolution, you can do Gibbs state preparation, and like there are some like maybe you can also, we are working on, you can probably also use the multiplicative weight update methods to solve SDPs using this method. So if you see these algorithms, why they seem to work is basically it's a common systematic strategy. Like for example, we have managed to also get an algorithm for singular value decomposition, and you will see an upcoming work from us on recommendation systems where we have removed many of those issues of the previous algorithms and so on. No feedback loop, nothing. So we have like if you see like there's this Krylov subspace motivated ansatz generation. The second step is sampling in a polyrotated basis on a quantum computer, and then you have a classical post-processing, and then you are done. And each of these states, like it can be like very nicely studied, and you can make a statement about them. And you will see more rigorous statements coming from us in future. Yeah, and there, like, you can measure, let's say, if you think that, my unitaries are not tensor polyunitaries, but let's say like uh, some k local unitaries, then also using some recent paper by Mitrai and Fuji from Japan, you can make statements about how to calculate this kind of psi u psi without the requirement of this kind of Hadamard test, which are basically illegal in the NISQ era. Like, I mean, you just cannot perform them, and calling any algorithm with Hadamard test as a NISQ algorithm, I personally do not believe that, like, that's in fact, I mean, you can call it a near term algorithm, but it's up to you. Like, I mean, maybe you think about 20 years as a near term, but yeah, that's very subjective. You can also calculate this kind of, like, over expectation values with 1 minus delta probability and additive error epsilon using this many number of measurements. And this you can get using something called Hopfding inequality and so on. And there are some examples which, like, I mean, we show that, this work, like, I mean, it's all trivially, like, I mean, you can talk to me later, like, I mean, we try different examples and so on, and we show that, like, it works, like, nothing very fancy here. Also, we show the examples where imaginary time evolution direct fails, but our algorithm, because you use the linear combination of structure, it like bypasses all those problems, and like it manages to find the answer. So with Jonathan, we recently implemented on the IBM Quantum Computer, and we like proposed something for the time-dependent Hamiltonians. And you can see that the QAS, I mean, so VQAS is the algorithm by Lee and Benjamin that takes like days for the implementation. Trotter takes like hours. On the other, our algorithm can be run in minutes. Actually, we can reduce it to seconds if we properly optimize and all, because the quantum computers just need to do some circuit sampling, and that's it, like and which can be done very fast. Like, I mean, that's what they are good for. And you see that, like, the worst performing ones is the Trotter one. After that, the VQS performs okay, but not very good. And our algorithm agrees like totally with the classically obtained values. Notice that this is for a very small system. We didn't go for a large system, like for comparison, because these algorithms, like variational quantum simulation, they require control unitary, and with the current devices you cannot have those control unitary. So while benchmarking, we like purposefully kept ourselves in the on the turf where these algorithms can at least play, and you can see that our algorithm like severely outperforms these algorithms. So looking in forward in future, you have to we hope to prove complexity theoretic results. We want to systematically reduce the number of quantum state defining the Ansatz. We want to demonstrate quantum advantage for practical use cases. And at the moment, I am like highly motivated, and I believe that maybe in the NISQ era, what you can do is this circuit sampling. And after reviewing like different papers and so on, it seems that like we can definitely like probably if we understand the structure of the Krylov subspace and all these ideas and so on, and reduce the noise and understand, do more rigorous study, probably quantum advantage could be possible. But yeah, I mean, it's we are still at the very surface level, and a lot of, I mean, like a lot of work needs to be done. And I invite the community to like join our efforts and ask questions and criticize us, and like see where are the like the chances for improvement, and like and work with us. So with that, I will conclude my talk, and yeah, like it's over to Kwek now.
Right, thank you. Are there any questions? So please feel free to ask Kishor to clarify something. Actually, there is a question from Ravi. Ravi, you want to ask yourself? You unmute yourself. It's a lot better if you do it directly.
Yeah, can you hear me?
Yes.
Yeah.
You have a question about performance. So you said you use K momenta. And for instance, I think the question says, what is the performance, and what do you say in with respect to NISQ, your expectation of momenta is? I guess that's a benchmarking issue too, but so what do you expect in NISQ? Say you need 5. That's a kind of a question that naturally pops up.
Correct.
Thank you.
Correct. I mean, you can see like we also mentioned here in the future work and all. So that's definitely, I mean, that's a very nice question. And you can see that this kind of analysis is basically related to this idea of Krylov subspace, which I mentioned earlier. So, I mean, so far, basically, this R that you see here, it's related to, the value of the K in the K moment and all. So, if we think about it, like so far we only compared against like the canonical standards like that people have been using, like VQE and so on and all. And our goal was basically to so far has been to like bypass those issues which people have been using with which people have been facing with the so-called best available quantum algorithm for the NISQ era. But to really achieve quantum advantage in the NISQ era, we need to compete against the classical, because the classical algorithms are super good. And for I mean, you need to ask like, what is the value of K for which you can hope to get some advantage? This is a very good question. And as of now, we do not have any clear answer. We have some intuition. So like, I mean, I will refer to some paper by Guy Kindler and Gil Kalai. So Gil Kalai, who recently gave a talk at CQT symposium, he has some paper where he proposes this thing called Kindler-Kalai hierarchy. And it seems that our work is kind of, like has some relations with the hierarchy that he has proposed. Like he has this hierarchy, we have also this hierarchy in K and all. And you see that, like, I mean, the problem of Hamiltonian, the ground state problem is QMA complete. So which means it's difficult for the quantum computer. But for a small value of K, it's easy for the classical device. So at some point, it will become like quantumly tractable, but classically difficult. Now, what is the value of K at which this happens? We don't know. So what we believe that we need to understand this Krylov subspace ideas more in detail. We need to understand this Kindler-Kalai hierarchy and make some rigorous statements using all these existing results to say what is the value of K. Can you systematically reduce, like can you use maybe, let's say, some approximate Krylov subspace, where what it means that you are not using all of the states from a particular moment, but depending on the value of beta, you only pick certain of them. And we are thinking that using ideas from reinforcement learning and all, where you have like this kind of tree structure, probably we can make some meaningful statement. But as of now, we are, I would say, not so sure. Like, I mean, what will definitely work. But yeah, I mean, we are exploring. And if you have some ideas or something, please feel free to email us. Like, I mean, we can also have meetings and like, I mean, talk and all, and definitely looking forward for some collaboration. Like, I mean, it's a very important problem.
Thank you.
Are there other questions? Yeah, I think sometimes you don't have to ask the top material, you can ask speculation in some sense. Mm-hmm. Are there other questions that anybody would like to clarify or to probe? This is a general talk, so I guess that
sorry,
this is more like a talk. Yeah, sorry. Yes,
go on. One quick question.
Yes.
For the talk. So how do you is there a systematic way of decomposing the Hamiltonian into the superposition of the unitary matrices? And can we always make sure that, okay, the R, the number of unitaries required is only polynomial, or is it necessary for that to be?
Yeah. So I mean, yeah, that's a very good question. And I mean, like I am. So normally, like I am being asked this question from physicists a lot, and computer scientists never question me, because you can write any Hamiltonian as let's say in the tensor poly basis, because that forms a complete basis. But you can like for example do like find this beta I by doing trace of like tensor poly, let's say with or any basis of unitaries with the Hamiltonian, and you can always decompose. So there is no problem with the decomposition. But you can ask that. But the second question which you ask is that, can I have like a small number of such terms there? Now, for a very wide class of Hamiltonians, like you have a small number of terms, like if you take like Ising kind of Hamiltonian or any two local Hamiltonian and so on, or any combinatorial optimization problem. I mean, like in fact, the two local Hamiltonian problem is a QMA complete problem, right? So that already is like a very powerful class of Hamiltonian. And many of the spin Hamiltonians and so on, they are given to you in this format. But then there can exist some class of Hamiltonians for which when you try to write, it does not have like efficient decomposition, like I mean as a linear combination of unitary. But notice that even in VQE there is this assumption like sitting there, because you are measuring there all of those Pauli string, if you remember, and then you use all of those Pauli strings to calculate the expectation value. You do not measure expectation value of Hamiltonian, you measure expectation value of the Pauli string, and using those expectation value and by the linearity you get the expectation value of the Hamiltonian. So basically, to implement any of these things on quantum computer, you need to have like Pauli number of such terms, and a very powerful full class and a very large class of Hamiltonians like naturally come in this picture. And we need to show like quantum, if we show quantum advantage for any of them, it's already a big victory. So yeah, I mean this is something which you can say that and a starting assumption for all of these VQE and like all kind of these Hamiltonians, like I mean like all kind of this ground state or Hamiltonian simulation or yeah, like algorithms.
Okay, so I kind of get the idea now. So basically we can just think of UI as the Pauli string, right? And that also the same as in the case of VQE, right? Because in the normal VQE, your Hamiltonian is expressed as the sum of Pauli bit strings.
Correct.
Okay. Thank you.
Right. Any other questions that you would like to ask? To clarify, share your opinion.
Yeah, you can criticize us. I mean,
no, the whole point is to criticize, right?
Yeah, I'm saying yeah, like without any
because we can only improve with criticism.
So I have a question. Maybe it's a question. So I guess can you say anything about whether or not, let's say you can decompose it to a series of unitaries, but I guess it's sort of a separate issue of how easy it would be to implement the unitary with like a series of gates, right? And you might potentially still well, I mean, I'm not sure if there's like just one unique way to decompose it, or if there's like a way to decompose it where your unitaries are very hard to implement, and maybe a way to decompose it where your unitaries are easy to implement.
Yeah. I mean, that's a very good question. So I mean, like depending on how you decompose, like it's like a basis, right? Think about a vector. You can like have different kind of basis in which you can write the vector and all, and it's basically some matrix basis, and you are writing your matrix in that basis. So yeah, I mean, depending on what kind of basis you choose, you will have problems or like easiness. So like I mean, like not like simple situation. So for example, I personally feel like the tensored Pauli basis. Why I like that? Because you can write any, let's say, qubit Hamiltonian in that format, and implementing those, like I mean, and the product of Pauli string is a Pauli string. So like I mean, if you have, let's say, some X tensor, Y tensor, Z, and you multiply with the other one, they collapse to one Pauli string. So basically, I mean, this is one of the reasons that our algorithm reduces to a sampling based algorithm. You can also use like k local unitaries, for which like I suggested that using this idea from the group from Japan by Mitrai and Fuji, you can perform some tasks like easily and all, like the Hadamard test and so on. But one can like think in an adversarial fashion and say that okay, I will come up with the different a difficult class of unit ray, like I will decompose like that. But yeah, I mean that will make the problem difficult, I would say, to like implement on the quantum devices. So for implementation on the quantum devices, it's better to like think in terms of the polystrings, because like I mean all of this X, Z and so on, like I mean a polystring can be like it's a bread and butter for the current NISQ devices. Like you ask Google, IBM, Rigetti, anybody, they can like implement it very nicely. So yeah, I mean, like I personally favor the tensor poly basis. And once you pick the basis, then you know that if you fix the basis, then any vector can be uniquely decomposed. So yeah, I mean, it's basically decomposition problem with respect to basis. But yeah, there can be many bases, and a basis can be a good basis or a bad basis. Now it's up to you. It's up to your experimental capabilities that which basis you will select.
Any other questions? I mean, Kishor is going to be around CQP. Yes. Just ping him on if you need to ask any pertinent questions. And if there are no more further questions, then perhaps we should end the session.
Can I add?
Yeah, sure. Yeah. Yeah.
Is there any dependence on the initial state side?
I mentioned that this choice of the initial state. So you see that, I mean, in VQ.
Oh yeah. Oh, so sorry. I didn't see it. Yeah. Okay.
No. It's good. It's good. You clarify, because it means that.
Yeah, it's good that
you miss that.
No, anyway, and it also means that you are following like the talk nicely. So that means the open question you came up with yourself. So that's good. Yeah.
That's right.
Yeah.
Yeah. Continue to probe, and even if you need some questions, do ask. Be sure. Any other questions? Anybody would like to raise some objections or some other viewpoint or something you have read about which may look vaguely similar, especially? Do you think there is anything else? Yeah, if not, then let's end the session. And thank you very much for joining us today for this wonderful talk, and Kishor in particular for preparing this talk.
Thanks, Greg.
Yeah.
And thanks,
Thank you very much. Yeah. Thank you. Bye-bye. Ciao.